Good morning, all. In today's session of operating system, we'll be moving on to the next topic related to page replacement algorithms. In operating system, we have various page replacement algorithms. One is related to first in, first out, optimal, and least recently used. And we'll be covering a topic related to thrashing. What is actually a page replacement? As the name implies, page replacement. What you want, we have two types of memories. One you have is your physical memory. The other you have is your logical memory, or you can even call it as a virtual memory, right? Now, in physical memory, as we have seen, because of demand paging or virtual memory concept, it is not required that all the pages of a particular process is to be present in your main memory. A part of the pages can be present in the main memory and the remaining part can be present either in your secondary memory, or we call it as logical or virtual memory. Assume here I have two pages P1 and P2 which are related to process 1. Similarly, you have two more pages P1 and P2 which are related to process 2, and I have one page related to process 3. So you are not storing all the pages of the process, any of the process onto the physical memory. And at a time, how many process are being present in the physical memory? 3. So the multi-programming concept is being increased because of this virtual memory usage. Now, I want when you are under execution of process P1 and P1 wants a next page which is P3, and this P3 is present in logical memory. What you want this page, particular page, to be brought into your physical memory. But when you see this physical memory, all the locations of your physical memory are being filled. So what you need to do, you need to select any one particular page either related to same process or any other process. You have to select this process, move that particular process onto the secondary memory, and in that position you have to make a move of the page which is being required. So as you see, the basic need for page replacement is you want a particular page to be brought from a secondary memory to physical memory. And because of pure demand paging or demand paging, so we have already seen what is a demand paging. So until a page is being required, you will not bring a page from secondary memory to logical memory, sorry, physical memory. Coming to pure demand paging, you start executing a process with no pages, and the first page itself has to be brought from logical memory to physical memory. So either demand paging or pure demand paging, you want a page. Now, in the physical memory, since you have these many pages, which particular page has to be selected for replacement? For that, we have various algorithms which we'll be seeing in detail. Now, the basic page replacement procedure, whatever we have covered in theory, I'll just go through in a pictorial representation. Assume you want a particular page, right? You to be brought into physical memory. So this is your physical memory and all of the physical locations are full. So you have selected, based on some algorithm, you have selected that you want to replace this page. So first, this particular page from physical memory will be moved into your logical memory, and after it is been moved into your logical memory, the corresponding page which is present in the page table, till now it was valid, now it will be made as invalid, indicating that it is no longer in the physical memory. Then the page which you want for execution will be brought from secondary memory to your physical memory in place of the page which is being replaced, and you will be resetting the page table accordingly. So these are the 4 steps that are required if you want a page to be moved from physical memory to logical memory. Now, when you want this page replacement to be done, or either in the case of virtual memory or demand paging, we need to be aware of two important techniques. One is frame allocation. You have to decide how many frames are to be given to each and every process, and which page replacement algorithm is to be used, so that you decide which page of the physical memory is to be moved into your logical memory. So for that we have three algorithms: first in, first out, optimal, and LRU. For either any of these algorithms, you need to provide some input. So the input that is provided for page replacement algorithms is nothing but your reference string. So reference string as it includes, it is collection of something, right? So here reference string is collection of pages. So it is collection of the pages which are being referenced in order. So if I write this, it means that after page 0, page 3 is being referred, page 4, 1, 2. related to some particular process, process 1 or process 2. So that is the input which will be provided to the algorithms, and will even provide the frame number of frames that are being allocated to the process. So 4 or 3 that are being allocated. So based on this input, we have to provide an output. The output is nothing but number of page faults. So how many page faults you are getting? What do you mean by a page fault here? You are trying to execute an instruction and that corresponding page is not present in the physical memory. So you call that as a page fault, or you call it as a page miss. If the page which you want to refer for execution is already present in the physical memory, then you call that as a page hit. So your job is to calculate the number of page faults for each of the algorithm. Now, coming to the first algorithm of page replacement, which is FIFO, stands for first in, first out. So when you go for this, the question will be given to you like this. Consider the page reference string. So this is your reference string. The pages are being referred in this order. With how many page numbers you are page frames you are allocating? 3 page frames. You have to calculate the number of page faults. So now just see here. So this is your frame, and what is the size of it? Frame size is 3. So initially you don't have anything in the frames because we are referring to pure demand paging. So whenever you start executing, only then bring the page. So now coming to the first page, what you want to refer? 1. So since 1 is not already present in the frame, you get 1 onto the frame. So since it is not available, we call this as a page miss, or you can call this as a page fault. So this can be also called as a page fault. So 1 will be stored. Similarly, the next page 3, it is not there already. So you will be dumping it into the frame. So this is also called as page fault. So this is your second page fault. Previously was 1 and now 0. Was 0 available earlier? No. So you also store it. So here you are storing it in the form of a queue. So here this will be 0. I mean 0 is brought in and the page fault would be 3. And the next page you want to refer is 3. So when you want to refer 3, you check it. 0, 3, 1. 3 is already there. So you need not bring it again. So this you call it as a hit. And now coming to 5. So 5 is not already there. So what is the previous frames that are available? 1, 3, 0. Since 5 is not available and you don't have any empty location here, you have to select one of the page, move it into your secondary memory, and after you move it into your secondary memory, you have to bring a page, right? So for that, among 130, which page, which 130, which one do I select according to first in? So which frame, which particular page was first entered into this particular queue? 1. So I select this page for replacement, and in place of 1 will store 5. So 5, 3, 0. The remaining order would be as it is 3 and 0. And since it is a hit, 5 is not present, so it is nothing, it is a miss. So the page fault would be 4. And the next reference string here is 6. 6. Check the content. 0, 3, 5. 6. Is 6 available here? No. So this is a miss and count it as 5. And among 0, 3, 5, which page would you select it for replacement? Among 0, 3, 5, which one has entered into the queue at the starting? It was 3. So 3 would be replaced with the current string or the value 6. The next thing is 3. So you have a value 3. 3 is not present among 0, 6, 5. So this is a miss or a page fault, which will be 6. The count of it would be 6. And among 0, 6, 5, which has entered into the queue at the starting level. So it was 0. So now 0 would be replaced with the current string. What is it? 3. So the number of page faults for this algorithm would be 6. So this is how you calculate for the given page reference string and the frame size, the number of page faults. Now, the main problem when you are going for first in first out page replacement algorithms is Bell-Addis anomaly. Now, as you could see, if this is my reference string and 3 frames I am allocating initially, assume I got 9 page faults. So what would be our impression? That if I increase my frame size to 4, so I'll be under impression that the page fault will increase. So if I am increasing the frame size, so what should happen to your page fault? Actually, the page fault should come down. But in reality, this will not happen. As you go for increasing your frame size, page fault would also increase. In which particular algorithm? FIFO. So this is the main problem you encounter in your first in first out page replacement. So that particular problem we call it as Baladi's anomaly. The next algorithm we'll be seeing in page replacement is optimal page replacement. So the input will be given as well as the number of frames. So here the number of frames are 4. So none of them are available. So the first 4 values will be dumped into it. 7, next 0, next 1, next 2. So the number of page faults still here would be 4. Now I want this particular value to be stored. So when you want this particular value to be stored, what you need to do is, what are the pages that are being present? So sorry, fifth value was 3, sorry 0. When you go for 0, 0 is already present in the string, so it is a hit. Now, after 0, what is the next value here? 3. So you want 3, but 3 is not present in 2107. So this will become a miss or a page fault. Now in this 2107, which is already existing, according to FIFO, I would replace 7. But here, what is the page that will be replaced here, because you don't have any empty location? What we do is, from 3, here you go for referring the future string. So when you refer the future string, you try to identify which of the existing pages, what are the existing pages here? 2107, which particular page is recently used, which particular page is less frequently used, or which will not be used for most of the time. So among 2107, 2 would be used, 0 would be used, 1 is not used, and 7 is also not used. But among 1 and 7, since it is not used at all, which one will you select for replacement? Now here we need to follow FIFO approach. So among 1 and 7, which one got into the queue for 7? So 7 would be replaced with the current value of the reference string 3, and the page fault will be increased. Next string is 0. 0, when I check with 2103, 0 is already present, so it is a hit. And after that 4. So when you go for 4, 2103 was my existing string. And since 4 is not present, you would count your page fault, increment your page fault by 1. But when you go for seeing here 4, 2103, there is no empty location. Which one would I select? So from 4, you select the remaining reference string. So when I am selecting remaining reference string, among 2103, which one particular page is not at all used? 1 is not used. So replace 1 with the current value 4. And when you check the remaining part of your strings, 2 is existing, 3 is existing, 0 is existing, and there is no page fault, and you need not replace it. So here in optimal page replacement, from the page which you want to refer till the end of the reference string, you identify which particular page is not frequently used. And if you are able to find 2 pages which are not been recently used, replace a page according to first in first out. The next algorithm which we'll be using here is least recently used. We consider the same input string, but here we'll take 4 frame sizes, and here we have to calculate the number of page faults. So in this case, as the name implies, least recently used, the first 4 frames procedure is same because my frame size is 4. So the page fault would also be 4 till you store all the 4 frames. Now my fifth frame is 0. So when you are getting your fifth frame as 0, 2107, 08th frame is already there, so it is a hit. Now you are coming for the next frame 3. So when you are coming for 3, 2107 is your existing frames or pages, and 3 is not there, so it is a fault. Increment your fault counter, and now you have to select a page for replacement among 2107. In optimal, you were checking in future which is a page which is less frequently used. Now here we'll be checking what is a page that is not being used frequently in the past thing, not in the future. So from 3, you check the past data. It means that the front data. You will not check the back data. You will check the front data. So among this 0, 2, 1 and 7, 2107, which one is less frequently used? In the sense, you identify a counter. 0 is being used twice. You check the front part of the data. 1 is used only once. 1 is also used once. The 7 is also used once, and 2 is also used once. Front part of the data. So among this, it means that 0 among 172, which one has entered into the queue at the starting 7? So you will be replacing 7 with 3. And 0, 2103, the next reference string, it is already there, it is it. Now we'll consider this case 4. My available frames are 2103 or pages 2103. 4 is not present, so fault will be incremented by 1. And which particular page you go for replacing, just from 4 you count the number of times the pages are being used here. So the front part you have to take it. So what are the values here? 0 is being used thrice, 3 is used only once, 1 is used only once, and 2 is only used once. So here 0 I will not count it because it is used thrice. And out of these 3, which one is used for, all of them have been used only once. So again you need to consider what is the page which is being entered into the queue at the starting phase of it. So after 7, 0 you will not consider, right? So after 0, what is the page that been entered into your queue? 1. So I'll replace 1 with 4 and you get your 4, and the remaining part of your values are already present in the string as it is. So you will be counting them just as your hit values. And the total number of misses when you count, it becomes your page fault, number of page faults. So in order to keep track of which particular page is to be replaced here, you either maintain a counter against each of the page or you go for stack based approach. So what you do in stack based approach is you just add the pages onto the stack, and whenever you are referring a page, move the page from the bottom of the stack and push it onto the top of the stack, right? So as you are referring the pages, move it from bottom to the top of the page, and when you are selecting a page for replacement, you only select a page which is present at the bottom of the stack. And the next topic here will be dealing is about your thrashing. So before going on to see what are the techniques and how you overcome thrashing, we'll see what is a thrashing here. Now, either we go for virtual memory or demand paging. What was the basic intention why we have gone for? We want more number of process to be present in the physical memory so that the multi-programming concept will be increased. But when you are going for this demand paging, you get a situation sometimes where as you go on increasing the number of programs, degree of multi-programming is increased, the CPU utilization will be coming down. So from one particular point of time, if there is a drastic decrease in your CPU utilization, the reason being they may be fewer number. You might store only one page of each process. Assume I have four process present, but in the physical memory I'm storing only one page. This is related to process 1, this is related to process 2, this is related to process 3, and this is related. So how many pages are stored? Only one page. So after executing, if I want another page, the CPU has to just go to secondary memory, find out the next page, and then swap in. So CPU, instead of performing a useful work, it is only using its time for swapping the data from one page to the other page. So the CPU utilization will come down, and the main reasons is insufficient memory. So we were under the impression that even if your program size is greater than the physical memory size, you still able to execute the program. Why? Because of virtual memory. So this is one case, and you want to improve the high multi-programming level, and because of poor locality of reference. Here locality of reference here is nothing but you want to first know when I'm assume I have P1, P2, P3 and P4 related to process 1. So you should have an idea of which particular pages will be frequently referred when you are executing a program. So that knowledge you call it as locality of reference, or you can even call it as principle of locality. So based on this, you will be only having that pages onto the physical memory, and remaining all other pages will be onto the secondary memory. So if that idea is not proper, then it leads to thrashing. How you can overcome this thrashing? So that can be done by using two models. One is your working set model, where you identify a parameter A, where A defines the number of frames that are required. So number of frames that are required for one particular process, and this is based on the principle of locality, right? And based on this a value A, you calculate your D. D is nothing but summation of WSS. This is working set model. Working set, if I have three process P1, P2 and P3, I have work set model 1, work set model 1, work set model 2, work set model 3, and each one will decide upon a parameter. This is A1, this is A2, and this is A3, where decide the number of frames based on your locality, principle of locality. So when I sum all of them, I'll get a value D, that is the total demand of the frames. So where that is the total demand, whereas M is the number of actual frames that is present in your physical memory. So when I sum up all of them, assume based on the principle of locality, process 1 requires 5, process 2 requires 4, and process 3 requires 3. Put together they are 12, but the available physical locations are only 9. So if that is the case, there may be a case that it leads to thrashing. But if your demand is less than or equal to the number of physical frames that are already existing, then we'll not be having any thrashing. And the next technique what we'll be using here is page fault frequency, where in page fault frequency for each of the process we construct a graph against the number of frames and the page fault rate. And if your arc is coming above, if your arc is above your upper bound, you increase the number of frames. And if your arc is below your lower bound, you decrease the number of frames. See to that your value is within this particular two lines between your upper bound and the lower bound. And whatever technique we have seen, it is related to your pure demand paging or demand paging. We even call this demand paging concept, where you are moving the process from one uh, physical memory to logical memory and logical memory to physical memory. We can even call that as a lazy swapper. Lazy swapper in the sense, until you require a page, you are not trying to getting into the physical memory. And instead of a swapper, since we are dealing with paging, we can even call it as a pager. So these are the techniques which are used to overcome your thrashing.